This section is showing a really useful technique for trying to remember equations, and it's called dimensional analysis. And it's making use of the fact that the units in an equation always have to work out. So anytime you have an equal sign, the units on one side have to be exactly the same as the units on the other. That's kind of like saying you have to compare apples to apples. You can't compare apples to oranges. The units on one side of the equal sign have to be the same as the units on the other. So if we're going to go ahead and figure out what is the velocity of speed of sound in a solid, what we can do is look at all the possible different quantities that this might depend on. So what I want is to see if I can combine these units, these quantities, to get something that has units of velocity. So remember, the square bracket means units of. So units of v are meters per second. So taking a look at some of these, K, the spring constant of the atomic interaction, that has units of newtons per meter, which is also a kilogram meter per second squared over meters, which is kilogram per second squared. M is the mass of a single atom, and that's going to have units of kilograms. The distance between the atoms, d, has units of meters. G has units of meters per second squared, or newtons per kilogram. And rho, the density, is kilograms per cubic meter. Now, I know that the spring constant has to be involved and the mass. The reason being, sound actually propagates via oscillations in the atoms. So it's going to depend on the stiffness of the spring. If you have a very weak spring, you wouldn't expect sound to travel very fast. On the other hand, if you have a very stiff spring, you'd expect that these atoms would push on each other very quickly and easily, and sound would travel. The reason I know that the mass of the atom is involved is because these are what's actually oscillating. These atoms are what are actually moving back and forth and causing the sound. And so let's take a look at those two and see what I can get out of that. So let's see. I've got kilograms per second squared from this, kilograms here. I know that velocity doesn't have that, so let's try and see what the units of KSI over MA, kilograms per second squared over kilograms, and that cancels out, and we just get 1 over seconds squared. Alrighty. Now I need seconds, and the only other seconds I see is right here, seconds squared, and that's just going to end up canceling things out. So I don't think that this one is going to be all that useful for me. What I can do is take the square root of this. The square root of this is going to give me 1 over seconds. And the only thing that's left is to add in a distance. So taking a look, I've got a distance here, and it makes sense that that distance would be a factor, because the sound is related to essentially how fast it takes to go from this atom to this atom to this atom, and so forth. So if the atoms are spaced further apart, you'd expect it would take longer for this atom to squash that spring, which would then cause this guy to move, which would then cause the next spring to squash, and so on down the line. So let me try square root of KSI over MA times D. And that's going to have units of meters per second. What do you know? So the speed of sound in a solid is the atomic spring constant, the springs joining the atoms, divided by the mass of the atom, this is the thing that's actually oscillating, times d, the distance between the atoms. And this makes sense. Now, just going off of units, we don't know that this is the correct equation, but it turns out to be. So really, there's two goals to this section. One is getting you used to the idea of using units to really see what the equations are correct or not. And I highly recommend that when you're writing out equations that you check your units as you go along, make sure they're the same on both sides of the equation. The other thing this section does is it gives us the speed of sound in a solid, and it gives us a better understanding because we see that the speed of sound depends on how close the atoms are, how tightly they are bound together, and the mass of the individual atom.